Okay, welcome everyone to this continuation of the theory of Lie theory, the theory of lies, whatever. I'm very excited today because I'm going to talk about one of my favorite topics. I feel like I say that every time. But anyway, I'm going to talk about one of my favorite topics. And why is it one of my favorite topics? Because it took me a long time to understand how important it actually really is. So when I learned it, for the first time, it was like the last week of an analysis class or something. And usually people don't pay attention in the last week anymore. So I didn't pay attention. And yeah, turns out it's super important. One of the cornerstones of modern mathematics. And we'll do it today. And the fancy name for it is Peter-Weyl. And the still fancy sounding but less fancy name is Fourier analysis. And we're going to do that. I'm going to explain how this relates. So yeah, if you're not paying attention in your last week of a calculus class, you maybe miss Fourier analysis, and it's really good. You're really going to do that. Anyway, so Fourier analysis, I will recall for you what that is. And you have seen it on R, but I will do it on S1, and S1 and R are really just the same. I take the line, bend it over, like in my picture up here, have some point at infinity. So S1 and R are the same. And the Fourier waves on S1 are just very easy things. Z equals to Z to the n. And why is it the same? Well, so let us remind ourselves of the Fourier decomposition. Probably I mean the Fourier series. That's what I want. Let's see, Fourier series. There you go. Blah, 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 blah. It's literally this idea. Oh, this is a good picture. Let's see whether I can zoom in. It's literally this idea to decompose some function, like here this funny square, into its frequencies. Oh, hopefully we'll see it here. So the square type thing is the sum over its elementary frequencies. There might be infinitely many of them, but that's fine. And the decomposition is called the Fourier series. Yeah, so you can decompose essentially any function into its amplitudes if you want. And in formulas, there's a lot of nice history. It's actually quite old, yeah? Actually quite old. And in formulas, hopefully we will find formula somewhere. It looks like that. So essentially every function can be represented as some fundamental frequencies here, e to the I pi, whatever. This is on the circle. Maybe you have seen it, so literally like that. Maybe you have seen it in the sine cosine form. So every function essentially can be represented as a sum of sines and cosines. That's literally what's going on up here, right? In this nice animation. Let's see whether the animation runs. So we have sum over all of them. Yeah, exactly. Everything is kind of a sum of sines and cosines, or equivalently of some exponential function, because literally the exponential function in the complex plane is just some sines. And cosines, we like that. So as I said, Fourier analysis, extremely important. Oh my goodness, I wasn't paying attention, and it actually doesn't matter. You can learn it later, but somehow please pay attention for Fourier analysis, because it's so important. Yeah. So here, literally, that's what we just saw, the cosines and sines, and this is just the Fourier analysis on S1. And the crucial observation here is now that S1, wait, S1, isn't that a Lie group? So you have some Fourier analysis on S1. And even better, these are our simple representations of the Lie group, S1. Interesting. So the Fourier decomposition is just literally just the Fourier basis, if you want. Yeah. So if you go back to this thing, where was it? Somewhere down here. So you express everything, maybe this is a little bit nicer in the exponential form. You express every function in terms of some scalars and some exponential thing. So this is literally the Fourier basis, if you want. Yeah, and so the simple representations of S1 form a Fourier basis of, classical calculus, if you want. And S1 is a Lie group. And in other words, for our Lie group S1, the simple representations form a Fourier basis of the classical Fourier basis. Maybe that generalizes, and yeah, so that's essentially, that it generalizes is essentially the Peter-Weyl theorem. So here the picture we had, right? So literally now a representation gives functions on G, namely in the following way. People call that the matrix coefficients. So for this example, there's nothing you need to do, but for higher dimensional thing, you want a function on G, and you do it as follows. You send every G to the this corresponding scalar product, where you have here the matrix given by the representation, matrix coefficients, and this gives you functions on G. And yeah, so for S1, nothing really happens. They are literally our Fourier waves, but for higher dimensional representations, we want to still have a scalar, and we do it in this way. So the pairing then gives us a scalar function from G to our ground scalar field C. Beautiful. And the interesting thing is that orthogonality of representations essentially forces these functions to be a Fourier basis of your space. That's literally what it is, right? Compact representations split into simples. The simples are orthogonal under the usual scalar product. Hey, that actually looks like, it should be on this page as well, but maybe I need to zoom out a little bit to find it. Maybe we can find it. Orthogonality, yeah, the usual, exactly this type. So that's how you get the Fourier coefficients, because it's essentially just pairing of the orthogonality of the basis in Fourier analysis. And the same holds here. The simples essentially form an orthogonal basis. So hey, we get this right on S1. It's this exact equation is literally why the Fourier transform works, right? So the Fourier basis is orthogonal, and what I'm saying here, that compact representations have simple pieces. The simple ones are already orthogonal, so we should actually see some form of a Fourier thing, but now for a higher dimensional object, and that's literally what we say. Yeah. So here, sine and cosines form an orthogonal set. That's literally what it is for Fourier analysis, and turns out we can do the same for an arbitrary Lie group, which is kind of nice. So Peter-Weyl theorem is literally just that. Functions on G have a Fourier series built from simple representations. Boo! So the way you usually do it is something like, okay, not all functions. I usually say all functions have a Fourier series. That's not quite right. There are crazy functions out there. Let's say L2 functions, whatever that means. Just all in a good sense. Yeah. So let's just say all in a good sense. All functions on G are built from simple representations via the matrix coefficients. It's what a literally great theorem. So representation theory, people always say like representation theory kind of generalizes Fourier analysis, and the Peter-Weyl theorem is like the poster child why this is the case. Yeah, and on S1 it's literally just that. Yeah, so it's really nice theorem, man. Any function on a compact Lie group have a Fourier series built from the simple representations. So any type of function you can now just express via the matrix coefficients. The Peter-Weyl theorem. Really, really cool. So I said again, kind of representation theory of Lie groups is somehow a generalization of Fourier analysis. Because for the simplest non-stupid Lie group you can think of as one, it literally is the Fourier theorem, and it works because of the orthogonality of our sines and cosines, and or more general, the orthogonality of representations of representations of compact Lie groups. Yeah, kind of like the orthogonality of characters, if you want, which I haven't talked about up to this point. So let's go through a slightly bigger example, SU2. So essentially, I think about it like this. So SU2, here my little group, has representations indexed by the natural numbers. So it goes on, not just doesn't stop at n, it goes on. So 1, 2, 3, whatever. And they all kind of play together. So they're the fundamental frequencies, if you want, of any function on the group. So these are then the Fourier modes of SU2. And I have infinitely many of them indexed by the natural numbers. And it works as follows. So we zoom into SU2 a little bit later, but roughly SU2 works as follows. SU2 is such a beautiful example. So it has simple representations for any natural number, including 0. I don't want to come up with a discussion here whether 0 is included in the natural numbers or not. With any non-negative, is that right? Non-negative integer is probably good. And they're of dimensions a little bit nasty. They're shifted by 1 by dimensions. So V0 has dimension 1, V1 has dimension 2, and so on and so on. And the matrix coefficients are actually pretty easy in this case. I'll show you them later. There's some nice sines and cosines, and these are then the Fourier blocks for functions on the group, which literally is this little type of picture. Yeah, so kind of a nice thing. And next time I will tell you more about these matrix types coefficients, if you want, in the form of characters. Anyway, please keep in mind Fourier analysis is important. Yeah, it's important. There are more important things in life than Fourier analysis, but it's one of the underrated things. Yeah, there are clearly more important things, but it's underrated. Please keep in mind underrated Fourier analysis, and Peter-Weyl theorem is a generalization. Anyway, I hope you enjoyed this video, and I also hope to see you next time.